Hi, in the last video you saw the application of the entire derivative on finding the volume of a surface of revolution obtained by revolving a region. Also you learned about finding the surface area, right, and arc length of a curve and surface area of a surface obtained by revolving a curve around a horizontal or vertical line, right? So in this section we very briefly, okay, this is the only video for 7.5 section, so where we use the integration to find out the work done by a force. So we will basically consider two scenarios. One is work done by a constant force and the other is work done by a variable force. Okay, so different force is applied at a different distance. Okay, on the constant force, work done by a constant force F is W equals to F times D, where D is the distance in the direction of the force. Okay, W is the work done, its units will be feet, pound or joule. Okay, force is the force, its unit will be pound or Newton. Okay, and D is the distance, its unit will be feet or meter. Okay, these first units for each of these variables are the so these units are basically the so basically the US units. Okay, and then the second units are basically the international units for the W, F and D. Okay, so if the force is constant, then the formula is W equals to F times D. When a force F is a variable force, the work done by F as an object move from x equals to A to x equals to B on a straight line is, you see that? How do you find out that? Is basically you divide that distance into so many sub distance and then you find out the force at each of the piece, like, right, like a constant force at each of the piece. Okay, and then you add the total work done at each of those pieces and then you add that. If you make those pieces tiny, very small, and then at that time the summation will tend to be an integral, right? So the total work done will be A to B F of x and then dx. Okay, so there are some laws that there will be another law that is a Coulomb's law, okay, so it is given in the book, you can look at that, but I'm just stating two of the laws here. One very famous is the Hooke's law. So this is for the spring. Okay, the force F required to compress or stretch a spring to additional length D is F equals to K times D. Okay, suppose you have, like, that's a spring, right? That's a spring, so original length may be L. Okay, so the force that requires it to stretch additional distance, so the force you need to stretch the additional distance D is always proportional to the length of that additional stretch, right? That is, F is proportional to D. So if you write F equals to K times D, where K is the spring constant. Okay, and the Newton's law of universal gravitation is the force of attraction F between two objects of masses, or you can write particles. Okay, that's okay to write particles instead of the objects. Okay, particles. So if you write particles of masses m1 and m2 is proportional to the product of m1 and m2 divided by the, and inversely proportional to the square of the distance between the objects, right? So F equals to G times m1 m2 over d square, where m1 and m2 have the units kilogram, D has unit meters, F has unit Newton, and G, with these units, G will the gravitational constant, which is 6.67 times 10 to the negative 11 meter cube per kg second square. Okay, so I am going to present just two examples here, okay, for this. So you might have seen these kind of things already in the physics, okay, because all of you are engineering students, so you might have seen that, but this is just the introduction, or basically just a very brief intro on how to use integral on the finding the work done. Okay, let us look at the first example. This first example has find the work done when a force of 112 units. You see that? That is given. No, 112 newtons. Okay, that is the constant force is required to slide a cement block 8 meters. Okay, so how to find out that is W equals to F times D. That will be 112 times 8, right? So that will be how much is that? 896 joules, right? Or Newton meters. You see that? All right. So the next example is this is question number 7 from the book. This is question number 11 from the book. There are very few problems as a homework, online homework. Okay. So example 11 is if a force of 20 pounds stretch a spring 9 inches, find the work done in stretching 1 foot from natural position. Okay. So in this problem is actually question number 11 from the book. So in this problem, we don't know the spring constant, right? So we need to find out the spring constant there, and then we will find out we'll find out the force there. Okay, actually, the force is. So what is force? So what is saying here is 20 pounds of force is required to stretch spring 9 inches, right? Find the work done in stretching 1 foot from natural position. So we use the Hooke's law here, right? So F equals to K times D, right? So F is 20 is required to move it 9 inches, right? So to move it 9 inches, you see that? So what do you get? So how much is 9 inches? So 9 inches is basically you need to change this to, let us change this to feet. Okay, so what do you get? So that will be, so that is basically K times 9 over 12, right? So you get, what is the K then? So K will, this is like 3 over 4 you get, right? So it will be 80 over 3. So K equals to 80 over 3, right? Now let us find out the work done. Then work will be how much? So it is stretching 1 foot, right? So let us do 0 to 1. Okay, and then how much is that? You 80 over 3 times D is, let's say that distance is x, right? Because you are finding the total work done when you change to when you move to 1 feet position, right? So that is x, and then when you do that, you will get 80 over 3 times x squared over 2, right? dx. So what do you get? And 0 to 1. So what do you get? That you'll be getting 40 over 3 feet per pound, right? Pound. Okay. You see that whenever you have that F is basically K times. So in this case, F will be K times X whenever we use the variable force, right? Here to find out the spring constant, you just use that F is 20 and K times D, and then you use that D that was given in the inch. So I changed into the feet, right? So K is 80 over 3. Now when you find out the work, it is 0 to 1 F of X dx, right? That's the formula, F of X dx. But what is F of X? So it is K times D is not a constant distance here, so D is so D is just X, right? In that case, D is X. So you find out F of X, that will be K times X, right? K times X, and then dx. So 80 over 3, and then if you simplify that, that's what you'll get. Okay, guys. So that's all for this section. So you can look at more examples in the book, and there are only a few problems. So there are some very easy examples on how to use the Newton's law of universal gravitation. So